All right, so welcome back to today's lesson. We have a little bit left to finish up in chapter 1 before we jump into chapter 2. So we ended yesterday talking about vectors and how to slide them around, add them together, and we finished yesterday with an example problem about Kevin McAllister stealing a toothbrush. So we drew out our vectors, we added them together, we found our displacement vector, and figured out what direction he would have to go in to return home. So I'm going to go ahead and share my screen with you now. Okay. All right, can you guys all see my PowerPoint? Yes, yes. Okay, great. So we're gonna give this initial example a try. Okay. So we have here an example. Naruto is running at 19 meters per second in a direction 105. Oh, sorry. 105 degrees counterclockwise from east. How should I set up my equations to find the components of his velocity? So remember, when we're dealing with a vector that's at some obscure angle, we can break it down into the components to figure out how far to the side it's going and how far up or down it's going. And those are called our components, our x component and y component usually. So think about this for a second. If 19 meters per second is our vector and 105 degrees is our angle, how should we set up the equations to find those components? Joshua, I see you raising your hand. Do you have a question? Okay, cool. Just hit the wrong button. Awesome. Quick question for you guys, technical thing. I've hit pause share. Can you guys still see the PowerPoint even when I've paused my share? Yes, great, awesome. That's the only way that I can actually see the chat screen. So I'm going to be pausing and resuming periodically. But awesome, you can still see. Okay, so let's think about this example then. I'm feeling A. A is in astrophysics. Nice, nice. Okay, so we know that dealing with components, we're going to be dealing with trig functions. Sine, cosine, tangent, all that jazz, right? And when we're dealing with trig functions, there's an argument of the trig function, right? It's sine of something. We can't have the sign of a velocity. That you just can't do that. You need to have an angle be the argument of a trig function. So right away we can automatically rule out C and D because 19 corresponds with 19 meters per second. That's our velocity. So C and D are incorrect for sure. Okay. Now thinking about A and B, we have to kind of visualize what's happening. If he's going at an angle of 105 degrees, does the sine correspond with the y component or the x component? So keep in mind, SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. The hypotenuse of our triangle is our vector 19 meters per second. And this y component is opposite our angle right here. Right. So A is our correct answer. North is our y component that corresponds with sine, and east is our x component that will correspond with the cosine. So good job, those of you who submitted your responses. All right, follow-up question to that. What do we do if we get an x component of negative 4.92 meters per second and a y component of 18.4 meters per second? Think through this one real quick. All right, I'm seeing some answers starting to come into the chat. That's great. So, first of all, is it okay to have a negative velocity? What do you think? Yes or no? Yes, yes, yeah, yes. Great. It is absolutely possible to have a negative velocity. Remember, a velocity is a vector, so it corresponds with both a magnitude and a direction. And the direction means, north, south, east, west, or forwards, backwards, left, right, up, down. Those are the directions that we're thinking about. So velocities have a direction associated with them. We can rule out A because it's not a scalar, it's a vector quantity. And when we want to talk about the direction of a vector, we could actually write out the word like north or west or something next to our velocity number. That's one way to go about doing it. But another way to go about doing it is putting a negative or a positive in front of our number, and that corresponds with the direction that it is going. So if we're dealing with the x direction, that horizontal direction, and we have a negative velocity, that just means, if we're taking the standard Cartesian coordinates, where we have our y-axis and our x-axis, positive x-axis corresponds with east, negative x-axis corresponds with west. So if we have a negative x velocity, that just means we're going west. Okay, so then C is our correct answer, which a lot of you got. Okay, another follow-up to the follow-up question. How do we find the magnitude and direction of the following velocity? So we have our x and y components there, and you can see I've written them out both ways. So Vx is negative 4.92 meters per second or 4.92 meters per second west. And same kind of deal with our y velocity. So how can we find the magnitude and direction of this velocity? Good, lots of answers coming in. Awesome. A for awesome. Yeah. So when we want to take the magnitude of our vector and we have the components, we use the Pythagorean theorem because it creates the right triangle. So remember, that is the square root of our x component squared plus the y component squared. That gives us the magnitude. And for the direction, it's the inverse tangent or the arctangent of y component over x component. We cannot just sum the velocities as they are. because we're dealing with angles. That simulation that I showed yesterday, we could just add the magnitudes together in that case, at the first case, because they were both going in either the exact same direction or the exact opposite direction. When we're dealing with angles, we can no longer just add or just subtract um, the magnitudes from each other. Okay, and yeah, the difference between A and C there, you have to be a really careful reader. Inverse tangent of y over x, not x over y. Okay, so here, I know we just did a little bit of review, but this wraps up chapter 1. So I want you to take a couple of minutes and think through these questions. This is kind of like our informal chapter 1 quiz. These are the types of questions that you would see on a quiz or a test covering this material. So I want to give you a couple of minutes to think through these questions, jot down your responses on a piece of scrap paper or something like that. You don't have to type them into the chat, but I want you to just take a second, think through the material that we've covered so far in chapter 1. It is foundational, so we are going to be building on it a little bit as we go. Okay, I'll stop talking and I'll let you think. All right. So hopefully that gives you a little bit of perspective as to the types of questions that you might be asked to do on a quiz or a test. These are, for the most part, conceptual problems. I didn't ask you to do really any calculations except for number 2, your height in centimeters. You probably know your height in inches if you are American. And if not, then you might already know your height in centimeters. But um, on a quiz or a test, you probably would be asked to do some actual manipulation of numbers and equations. Um, but this just, again, is supposed to be a little snapshot about conceptually what you should understand about chapter 1. Oops. Okay, so I showed you this slide yesterday, the bonus activities, if you want a little bit of extra practice for this particular part of chapter 1, vectors. There are those 3 resources for you on Canvas that you can check out. I'll be posting answer keys to those on Friday at some point so that you can check your work if you decide to do them. All right, before we move into the chapter 2 PowerPoint and get started on that, do you guys have any questions about chapter 1? Yeah, Kelsey, I wish the US would completely switch to metric 2. That would be really helpful. Um, but unfortunately not. Okay, if you're nervous about this chapter being foundational, I just mean that in the context that it's something we'll use pretty regularly. Units and vectors are present in almost every chapter that we'll be going through. So you'll see it a lot. If it's something that you think you might struggle with, I recommend that you do some of those practice resources. But again, you'll see them in context later on, and that might help your understanding as well, seeing when you would actually apply this vector math as opposed to just doing it for the sake of doing it. So hopefully that will help. Okay, well, I'm going to go ahead and open up our chapter 2 PowerPoint. Give me one moment, please. Oops, so sorry. One moment. Someday I'll get the hang of this. Okay, can you guys all see my chapter 2 PowerPoint with Kitty? Yay, good. All right, we're getting there. So we're gonna start talking about chapter 2, motion in a straight line. We'll do motion around curves and throwing things later. That'll be next week. But right now, it's just motion in a straight line. So here we go. All right, describing motion. How do you know something is moving? It's kind of a weird thought to consider, like having to actually describe that. So type into the chat what you think would help you know something is moving. Colby, if its position is changing. Gabriel, point of references. Joshua, if it has a velocity. Cool. Although 0 is technically also a velocity, but I get what you're saying. Vincent, change in position over time. Kelsey, point of reference. If you were in space, you couldn't really know. Interesting thought. Point of reference. Yeah, those are some great thoughts, and we will incorporate some of those momentarily. Displacement margin. Wow, look at those fancy words. Gauge readings. If it changes position. Nice, nice. Okay, so by the end of this chapter, you should be able to answer some of the following questions. How far does an airplane travel down a runway before it reaches takeoff speed? When you throw a baseball straight up, how high does it go? And when you drop your phone, how much time do you have to catch it before it shatters on the ground? Pretty practical things to know, I guess. So those are kind of the goals of what we're going to be able to answer by the end of chapter 2. Okay, so when we want to analyze motion, it's helpful to set up a coordinate system as a frame of reference, like you guys were saying, a point of reference. So when we create a frame of reference, we're creating a coordinate system. And usually our coordinate system will look something like this, like a Cartesian coordinate graph axis deal. It won't always look like that, but most likely that's just going to be the simplest way to look at a coordinate system. Okay, a coordinate system is helpful because it defines where an origin is. And the origin is the place where both of your variables, your x and your y variables, are 0. Also, your 0 point is another way to think about it. It also establishes which direction is positive. So usually we're used to seeing this up and right are positive, down and left are negative. But really we can choose whatever is most convenient based on the situation. As long as you keep it consistent throughout the entire problem, you could say down is positive if you wanted to, as long as you keep it consistent. So a coordinate system is helpful for that. And we're interested in usually the position of the object. So the position is the separation between the object and the origin. And when we're dealing with motion along the x-axis, we'll call that the x value. Okay. We're always going to refer to horizontal motion as in the x direction and vertical motion as in the y direction. Again, just for the sake of consistency with math classes and things like that. All right, speed and velocity, we talked about that yesterday. Speed is a scalar, so it just has a size, right? Just 75 miles per hour, while velocity is a vector where the direction matters. So if you're driving your car, you have your speedometer that tells you how fast you're going, and some fancy cars, mine doesn't because it's not a fancy car, but some fancy cars have the little like compass thing on the, usually the rear view mirror, that tells you whether you're going south or east or whatever. So if you have both a speedometer and a compass in your car, that tells you your velocity. right? Because that tells you how fast you're going and what direction you're going. So both of those things together are a vector. Velocity is a vector. Speed is a scalar. And again, just for the sake of repetition, pounding this into your brains, usually right, east, north, forward, and up are all positive directions, and left, west, south, backward, and down are all negative directions. I put 2 negative lines there just to make it a little bit easier to see, but it just means negative. Okay. And again, we can change that if we need to for convenience in the problem, but that's our typical setup. And there are actually different kinds of velocity that we'll be going through today. So the first type of velocity that we're going to talk about is average velocity. So this is total displacement divided by total time. That's also another way to think about it, is the rate at which an object changes its position from one place to another. It's also a vector quantity because it is a type of velocity, and the units of it are some distance unit divided by some time unit. So that could be meters over seconds, miles per hour, kilometers per hour, just some distance divided by some time is the unit for average velocity. So here in the green dashed box, I have the equation for you for average velocity. V average is triangle x over triangle t. That triangle is actually a Greek letter named delta, and that means the change in. You might have seen it in chemistry or something like that. But when we calculate the change in something, we take the difference of those 2 points. So if we're talking about the change in x, we have x2, our second point, minus x1. And our change in time is our time 2 minus our time 1. The difference between those is what that triangle delta means. Okay. So thinking about a practical example, if it takes 3 hours to drive 300 kilometers to Miami, what's your average velocity? Type it in the chat. If it takes 3 hours to drive 300 kilometers to Miami, what is your average velocity? Great, yeah, good. 100 kilometers per hour. And yeah, I noticed that one of you didn't put your units in and then you added them in later. That's great. We always want to give our answers with units so that we remember what it is we're talking about. Great, 100 kilometers per hour is our average velocity. If you drive to Miami and you spend the day there and then you drive back, what is your average velocity? Think about it. If you drive to Miami, spend the day there, and then drive back, what is your average velocity? Sure, day is in 24 hours, yeah. I'm seeing some different answers. And that's great. Let's think about this. What is the difference between displacement and distance? Do we remember? The difference between displacement and distance. They don't mean the same thing. So we talked about this yesterday. Distance refers to our total distance, like all of our pathways added together. So if it's 300 kilometers one way and 300 kilometers back, our distance is 600 kilometers. Our displacement is only concerned with where we started and where we ended up. So if we started at home, went to Miami, spent the day there, ended up back home, our displacement is 0. because we started and ended up at exactly the same place. So no matter how much time you spend in Miami, whether you drive there and then drive straight back, or drive there, spend the day, and then drive back, regardless of how much time you spend there, if your total displacement is 0, your average velocity is 0. It's nuts. But that's physics for you. Okay. So let me take a look at some of these comments. I see you guys typing to each other. Distance, how far you travel. Yeah. Displacement is not velocity, but displacement is related to velocity. Remember, velocity is your displacement divided by your total time. But 0 divided by anything is 0, no matter how much time you spend there. Okie dokie. Okay, great. So average velocity. All right, we're gonna do an example of this together. Okay. A race car starts a race. 1.0 seconds after the start, it is at a 0.19 meters from the starting line. And at 4 seconds, it is 277 meters from the starting line. What is its average velocity during this time interval? All right, so take a second. If you have your calculator handy, give this a try on your own. I know I don't have the cat picture there. We'll go through it together, but I want you to give it a try real quick. Good, I'm seeing some answers coming into the chat. Woohoo! So let's set this up together. All right, there's our picture. It's like, it looks super overwhelming because it's from the textbook, and they just have a lot of information in the pictures. But here we have our race car. You can see the starting line there. The first point that we're interested is that position of 19 meters. And the ending point that we're interested in is point 2 at 277 meters. So average velocity is our change in position, our displacement, divided by change in time. So 277 minus 19 over 4 seconds minus 1 second. And that gives us an answer of 86 meters per second, which is what I'm seeing in the chat. So great job, guys. Okay. So some rules for average x velocity, and I'm just going to keep it in the x direction just because we're dealing with motion in one direction, motion in a straight line, and it's easiest to think about it flat ways before you start thinking of it vertically. So we're just going to talk about the x velocity right now. V average x is positive if x is positive. Remember, x means position. If x is positive and increasing, then we have a positive average velocity. If x is negative and becoming less negative, so it's moving towards 0 on our axes, then we have a positive velocity. So anytime the particle is moving in the positive x direction, we end up with a positive x velocity. So on the flip side, our average velocity is negative if our position is positive and decreasing, or if our position is negative and becoming more negative. Anytime it's moving in the negative x direction, we're going to end up with a negative x velocity. So remember, you can choose the positive direction to be whatever is convenient for the problem, as long as you keep it consistent the whole time. And there will be times when I'll use down as positive instead of up. We're not there yet, but keep it consistent. Okay. So when we're visualizing motion, one of the most helpful ways to do so is to create a graph. And we call these graphs of motion xt graphs or position time graphs. Remember, x is position. So I put there a reminder of our average velocity equation, our change in our x position over time, our change in time. And if we create a graph of that motion, it's called a position time graph or an xt graph. Okay, so here are axes that we would use for creating a graph. And in this case, it's a little bit strange to look at because in this case, x is not the horizontal axis. Because x does not stand for x direction, x stands for position. It's a variable, it's position. So our position is actually the y-axis, and time is along the x-axis. It's strange. So that's why people tend to call it a position time graph as opposed to an xt graph. But this is what the setup looks like. Vincent, you have a question. Wouldn't it just be change between the start and end point still? Yes, that would still give you your displacement. Colby, you learned that S stood for position. That's true in some cases. Some people use different variables for position. Some people actually write out the word position. Our textbook, I believe, at least the one that I'm referencing, I believe most commonly uses X as position, which is why I did as well. But S is also valid as a choice. All right, so I put here like a bird's eye view of our race car. And remember, point 1 was at 19 meters. It wasn't right at the starting line. So I shifted it up a little bit from our axis. And if we want to think about what this car is doing over time, the position graph would look like a nice curve. Because if you think about it, a race car, once it starts a race, it's like stopped at the starting line, and then they give you the green light or the wavy flag or whatever it is that they do, and the car starts moving. But a race car, any car in general, can't just like go from 0 to super fast instantaneously. It takes a little bit of time to speed up or accelerate off of the starting line. So at the beginning, it doesn't cover very much time and very much distance per second. But as it speeds up more and more, as time goes on, it can cover more distance every second. And so we see a graph of its position looking like a nice, smooth curve. Turbo has to kick in. Yeah, true. That NOS, whatever. I don't know. My husband's super into like Fast and Furious stuff. I'm not, clearly. But anyway, yeah, turbo has to kick in, and they start speeding up to win the race. So this is what the position graph would look like for our race car, right? It starts off slow and then gets faster and faster. And so we end up with this nice curve. This is the textbook version of that same graph. A little bit more detail for you there. We can see they've marked our point 1 and point 2 that we were interested in before. And remember, average velocity is our change in position over change in time. Position is our y variable. So if we're changing our y variable divided by changing our x variable, that's the same thing as calculating the slope of the line connecting those 2 points. If you remember from math classes in school, I don't know when you learned this, Algebra 1 maybe in school, slope is rise over run. So how far up the 2 points are, the difference between those, versus how far over, rise over run, y over x. Delta x over delta t. Look at that. So the slope of a position time graph actually gives you the velocity in the x direction. That's going to be a really important thing to remember. If you take notes on these lectures, write that down, put a star next to it. This is going to be a key concept that we come back to over the next couple of days. The slope of a position time graph gives us velocity. Okay, that change in position over change in time. Okay. The second type of velocity that we are interested in is instantaneous velocity. And that's how fast an object is moving at any particular point along its path. So we're not necessarily interested in how fast is it going from this point to this point, our average velocity. We're looking at how fast is it going at 3.58 seconds. That one instant in time would give us our instantaneous velocity. And usually we just call that velocity. I don't know if that's because instantaneous velocity is a mouthful, or if that's just really the velocity that we're always interested in. But we'll just call that velocity. We'll call the other average velocity, and this is velocity. But really the way to think about instantaneous velocity is that it's the average velocity between 2 points as the time interval between them approaches 0. So as those 2 points get closer and closer together, what is the average velocity between those 2 times? And so really what we're dealing with here is a limit. As the change in time gets smaller and smaller, as it approaches 0, what is the change in position over change in time? So that's the way we write a limit, lim, as delta t approaches 0. And it's the limit of that change in x over change in time. And the shorthand way to write that is dx over dt. D kind of, just remember it in terms of like d for delta, because they're related to each other. But dx dt is actually a derivative, which is calculus. So as this change in time gets smaller and smaller and smaller, and we still want to figure out how fast it's going between those two really, really, really small time increments, what we're going to be doing is introducing calculus. The derivative of x with respect to t, dx dt, the derivative of x with respect to time, all of those mean the same thing. And in this case, they mean the instantaneous velocity. So let's put that in context. Okay, here we have our race car, the overhead view again. And this is the graph that I had showed you before, right? Our nice curve as it speeds up and tries to run the races. Turbo kicks in or what have you. So as time goes on, the interval of time between our 2 points of interest shrinks, and the slope connecting those 2 points gets steeper. So this is what we saw previously. And as those 2 points get closer and closer together, as that time difference shrinks, the average velocity, the slope of that line connecting the points, is getting steeper and steeper, until we get to this point, this black line, where that line is actually only touching our position curve at that one point. You can see, I'll go back. You can see in this case, our line that's connecting those 2 points is actually touching the curve in 2 places, right? At those 2 points of interest. Same thing here. At those 2 points of interest, the line cuts through the curve. At those 2 points of interest, the line cuts through the curve. But here, when we've narrowed it down to only 1 point of interest, that line is only touching the curve at that one location. And that's called a tangent line. If it's tangent to the curve, that means it's only touching the curve at that one particular point. So this would be, there's no space at all between these 2 points of interest, these 2 positions. And our line only touches the curve at that one point. That's called the tangent line, and the slope of that tangent line, that black line, is our instantaneous velocity, or the velocity of the object at that particular instant. That point, that black point, would be our point of interest, our instantaneous velocity. So that black line, our tangent line, that's a derivative. Congrats, you've done calculus. If we can find the slope of that black line, that's calculus. Hey, that seems an awful lot like algebra because it's just the slope of a line. Yeah, you're right. Calculus is like fancy pants algebra a little bit to start out with. So if we can find the slope of that tangent line, that's a derivative. That's our instantaneous velocity, how fast it's moving in that particular instant. Do you guys have questions about that before I move on to the next slide? All right, I'm getting some nopes and some nops and some all goods. Cool. So if you do have a question, type it in the chat. I'll monitor. It's off to the side there. All right, great. Feeling good. So just a quick note on the signs of these velocities. A time interval is always positive. We can't actually go back in time. So time interval is always positive. We'll always be going forward in time. Okay, but our velocity is going to have the same sign as our change in position. Excuse me, because we can move backwards in space, right? We can move forward, backward, left, right. We can move around our position. So our velocity is going to have the same sign as the change in our position. So a positive velocity, instantaneous velocity, remember, positive velocity means that our position is increasing. Our motion is in the positive x direction, and so we'll end up with a positive slope of our line, our tangent line. So that would be the case if the object is like moving forward, like our race car driving forward. And there are a couple of examples of what position graphs would look like if we're dealing with an object moving forward with a positive velocity. So you can see the top one is labeled position time. The bottom one is labeled distance time. You'll see these labeled all kinds of different ways. You saw XT graphs, ST graphs. You'll see them all different ways, but they all mean the same thing, right? The position, what the object is doing over time. So in that top graph, if we were to draw the slopes of our lines, can you guys see my mouse moving around on my screen? Yes, okay, great. So if we were to draw a tangent line down here at the bottom, it would have a very shallow slope. But if we move to different points along this curve, the slope of our tangent line would get steeper and steeper, right? So that means our object's velocity is getting bigger and bigger, because remember, velocity is the slope of that line. So we're starting off slow, our velocity is getting a little bit bigger and a little bit bigger and a little bit bigger. This top would be the case of our race car starting a race and speeding up. That bottom graph there, if we draw a tangent line, it starts with a really, really steep slope. And then if we pick a different place, our slope is shallower, less steep, and less steep. So our velocity is getting smaller and smaller. This object would be slowing down, like the race car at the end of the race. It starts off really fast and then it's getting slower and slower, still moving forward though. It's just getting slower and slower. A negative velocity in the x direction means that our position is decreasing, or motion is in the negative x direction. That would give us a negative slope in our position time graph. So that would happen if the object is moving backwards towards the starting line. We might get a graph that looks like this, right? So we're starting off with a tangent line that's that's pretty flat, and then it gets steeper and steeper, but it gets steeper negatively, right? It's pointing down. So that would be if the object starts at a really far position and moves backwards towards the starting line, right? Its position is going from a high number to 0. So that would be like if you started in front of the starting line and then your car was in reverse and you went backwards. You sped up backwards. Yes, Josh, speeding up in the opposite direction, opposite position. That would be exactly the case of what's happening in this graph. It's speeding up but driving in reverse. An object can have a positive position and a negative velocity, like we see in that bottom graph. Or vice versa, it can have a negative position and a positive velocity. Remember, the position just tells us where the object is with respect to our origin, our starting line, and our velocity tells us how it's moving, like Mater in Cars. Yes, my son is in love with cars right now, so yes, absolutely. Good connection. Okay, so shapes of these position time graphs. There can be all kinds of different shapes to these. There can be flat lines, straight diagonal lines, curved lines. You can have several of these in the same graph, just different, like all kind of mashed together. Like it'll start off flat and then go like, and then it can just get crazy. But they have all different kinds of shapes. You still approach them the same way. No matter what the shape of the graph is, velocity is always going to be the slope of that position time graph. So remember, slope is rise over run, or the change in our y variable divided by the change in our x variable. If the slope gets steeper, either positive or negative, then the velocity's magnitude is increasing. So the object is speeding up, either speeding up going forward or speeding up going backwards. If our line is getting steeper, then it's speeding up somehow. Okay, so here's an example of a position time graph. What is the velocity of this object? Take a quick second, think through it. We'll go through the answer together in about 20 seconds. All right, great. I'm seeing a lot of answers coming in. I'm seeing a lot of the same answer coming in. I'm seeing a lot of the same correct answer coming in. Good job, guys. So the velocity is the slope of this line. The slope is rise, so how far up it goes. Over run, how far over. It goes up from a position of 0 to 50, so 50 minus 0. And it does that in 5 seconds. So 5 minus 0. So 50 divided by 5 gives us 10 meters per second. Okay, here's another one that I want you to give it a try. What is the velocity of this object during each stage of its motion, according to this graph below? And then what is its average velocity over the whole trip? So I'm going to give you a little bit longer time to answer this question. You'll end up with 4 different answers when we come back together and go through it. So take just a moment. All right, so it looks like a lot of you have come to some conclusions here about the motion of this object. So let's take a look at it together. We can see here that this position time graph is clearly in 3 separate sections, right? There's that first section and then a flat section and then a third section there. And we have to look at each of those separately because they have different slopes. So stage 1, that first part of the graph, the slope of that would be, if we look at the change in position, it's going 5 meters in 5 seconds. So that gives us a slope of 5 over 5, or 1 meter per second. Stage 2, its position is not changing as time goes on. Whenever you see a flat part of the curve, well, we call it a curve, even though it looks like a plateau. But whenever you see a flat part of the curve like that, that means its position is not changing over time. So that means it's standing still for that time interval. All right, so the slope of a flat line like that is 0. It's not changing its position, even though 5 seconds have passed. The slope is 0. Stage 3, if you look at the slope, we're starting at a position of 5 meters and going back to a position of 0 meters. So 0 minus 5. And we're doing that in the time frame of 10 to 12 and a half seconds. So 12.5 minus 10 seconds, that gives us a slope of negative 2 meters per second. And remember, that negative sign gives us a clue about what direction it's traveling. It's traveling back towards the starting line, or back towards the origin. If you want to think about the average velocity, remember, average velocity takes into account its total displacement. So if it starts at a position of 0 and ends up at a position of 0, then even though it traveled some distance between those 2 points, we still end up with a displacement of 0. And so our average velocity is 0 meters per second. So it looked like a lot of you got that. You came to those conclusions, which is great. Good job. Remember, always you must include the negative signs in your answers, because that tells us about the direction. Okay, so still thinking about this, what is the object's total distance and what is its displacement? Good, some answers coming in. Awesome, and they are all in agreement. The distance that it travels is 5 meters forward. It stops there and then travels 5 meters back. So its total distance is 10 meters. But its displacement is 0 meters. As I was saying, it starts at a position of 0, ends at a position of 0. Since it's ending up at the same place that it's starting, its displacement is 0. Okay. All right, take a look at this graph now. Describe in words what is happening to this object that creates this graph, both its position and its velocity. So I don't want you to calculate it. I want you to describe to me what is happening with this object. Ooh, Aaron, I like that you put it in like a real life scenario. That's cool. Okay, great. So you guys are thinking through it. Great. So let's go through this together, and you can kind of check yourself, see how you did. So let's think about its position first. Okay. the object moves away from the origin, right? Its position is increasing, it's moving forward, maybe away from the origin for 10 seconds, and then it comes back towards the origin for 10 seconds. That's what its position is doing, is moving forward and back, or that sort of thing. Velocity. We know that the object has a positive velocity at first because the slope of the line is positive, and then the slope gets shallower and shallower until at the top of that curve there, the slope is 0. And then it gets negative and negative and more negative. So that means it's going pretty fast, it's slowing down and stopping, and then it's speeding up again in the opposite direction. So I really liked that example. Maybe you guys saw it in the chat. Aaron's example, the dog runs for a stick and then goes back. So the dog starts off going really fast for the stick. It has to stop while it picks it up, and then it comes back to you. That's a really great way to think about it. Marco, you said a car sped up until it slowly started slowing down, until it started going in reverse. That's another interesting way to think about it too. I would caution you guys though about just looking at the shape of the graph and thinking that this, like, since it looks like a vertical curve like that, that it must be somebody throwing a ball up in the air, then it lands on the ground. It absolutely could be, but we can't just look at the shape of the graph to kind of assume that it's some kind of like forward projectile, that we've thrown something forward because the graph looks like it's arcing forward. We can't just assume that because its position ends up at 0 again. So it's something that ended up at exactly the same point that it started at. So this could be like Indigo says, throwing something straight up in the air. Absolutely. If we throw it straight up and then it comes back in our hand again, that might be the position time graph for that particular object. But it would not be the position time graph for somebody throwing a ball forward. Does that make sense? Do you guys see the difference between those two scenarios? Okay, I'm seeing some yeses. Great. Great, yeah. Since the position ends up at exactly the same position, the object has to end up at the exact place where it started. It's a yo-yo. That's a cool one. I like that. Okay. We don't know if it's a vertical position or horizontal position because it's a 2D graph. That is correct. Yeah, we could be talking about vertical motion or horizontal motion. It's not specified. Absolutely true. Which is why it could be a dog or a yo-yo. Great. All right, so just a really quick review. We're almost done for today, just about 5 minutes left. So quick review of these two different types of velocities that we've talked about so far. This picture is from the book. So we can see here in that first picture on the left, we have a nice curve, 2 points that we're interested in. If we want to find the average velocity between those 2 points, we would draw a line connecting those 2 points and find the slope of that line. So our change in position in that first case is 150 meters. Our time interval, change in time, is 2 seconds. So that gives us an average velocity of 75 meters per second. Let's take an even smaller time interval. So instead of 2 seconds, now we're looking at 1 second. We're moving those points closer and closer together. So as our time interval is 1 second, the change in position is only 55 meters. And so that gives us an average velocity of 55 meters per second in that particular time interval. And if we keep moving those points closer and closer together and drawing a line between them, we end up with the tangent line, or the line that's touching the curve at just the one point, which makes it instantaneous velocity, because we're just looking at the velocity at that one instant. And in that case, the slope of our tangent line is 160 meters over 4 seconds, or 40 meters per second at that one particular instant in time. So that summary key bullet point at the bottom there, at any point on a position time graph, the instantaneous x velocity is equal to the slope of the line that's tangent to the curve at that point. And we can see if we move that point farther along the curve, the tangent line would get steeper and steeper, meaning that we would have an increasing velocity, because the magnitude of the slope corresponds with the magnitude of the velocity. Okay. And then this last picture that I have to show you here is a graph that has several different sections. The example that we did together was more angular and linear and nice to calculate. But this would be clearly a smooth curve where we would be taking the slopes of the tangent lines. So at points A and B, the slope of that tangent line is positive. At A, it's a little bit shallower, and at B, it's steeper. So that means it's moving faster at B. At the top, the tangent line is flat, so the velocity is 0. The slope of a flat line is 0. And then the velocity is negative because the slope is negative and still negative. Okay. So when we look at these position time graphs, we look at each section individually and think through what that means about the motion. All right. Any questions, comments, concerns that you guys have about this material? All good. Kitty. Yes. Okay, great. Great. Colby, much better than those nasty unit conversions. Yeah, I agree. I think this is easier to visualize because it's a visual thing, as opposed to units and conversions, which are much more of a mathematical thing. So sometimes visualizing it is a lot more helpful. Well, great. We are going to pick up here tomorrow and talk about velocity time graphs and acceleration. So yeah, if you guys have questions about this material, or if you have other questions about FIT or that sort of thing, I'm going to stop the recording, but I'll keep the Zoom open for a few minutes. So if you have any questions, you can feel free to ask. But if not, you're welcome to go, and I hope you guys have a great day.